So I guess just maybe, as far as so I mentioned this last time, but I'm going to keep exercise sets for at least a few weeks. And then at some point, so the main deliverable for the course is a project, at least for those of you taking it for a letter grade. So I'll probably start posting topics probably in week 4 of the class will be my guess. I just want to mention it now because I'm definitely happy to have people propose their own projects. So if there's either something from other research you're doing you think would work well with this class, and you could kind of have it be a win-win, get a project, get credit for this class, but also have it be good for your own research group, that's cool. Or if there's already something that's triggered intrigued you, that's happened so far this quarter or happened sometime last quarter, maybe just start thinking about that in the back of your mind. But I mean, I'll give out enough concrete project topics for everybody in a couple weeks anyways, okay? Oh, yeah, right. So I should have done this last week, but I forgot. Because we're putting the videos up on YouTube, I'm required to get a release from all of you. So pass these around. So this says, you agreed to either one, have your likeness appear on a publicly available video, or if you don't agree to do that, then you agree to sit somewhere in the classroom off camera, and that's fine. So most of the class is off camera. You may have noticed. So
we were just on the new course, do we need to sign it?
I think you do actually, right? I'd feel better if you did. So yeah, good. Okay, so it's been a week, so let me just sort of remind you where we left off last week. So this first segment of the course, I'm thinking probably the first 3 weeks, is all about the theory of ascending auctions. And so what we're doing is we're designing ascending auctions for increasingly complex scenarios. Okay, so each of the scenarios I'm choosing to unveil, a new layer of complexity in the design of ascending auctions. So we're in the middle of what I've been calling scenario 3. So scenario 1 was unit demand bidders and identical items. That was easy. You just use a single ascending auction. Scenario number 2 was non-identical goods, but additive valuations. That was also simple. You just use parallel ascending auctions, although we saw already we needed to introduce ex post instead of dominant strategy implementations. Now we're in scenario 3. And the good news about scenario 3 is we can get very striking positive results. We can get pretty much everything we want. They're great ascending auctions. The bad news, or maybe it's a feature if you want to call it that, is it's actually quite intricate to, even though the solutions are simple, understanding why these simple solutions work so well is pretty intricate. So we already saw some non-trivial theory of this scenario last lecture, and we'll finish that up this lecture. So again, what is it? So we have non-identical items, and we talked about motivations last week. And we're going to assume bidders are unit demand. So if you give them a bunch of items, they throw out all of the ones except their favorite. So there's a private value Vij for each bidder I and good j, and if you get a bunch of them, you just take the max. So that means without loss, we can think only about allocations where each bidder gets at most one good, i.e. we can think of allocations as matchings in scenario number 3. And again, what are we shooting for in all of these scenarios? We want an auction, that's the analogous of dominant strategy incentive compatible, but as we saw in this context, it should be ex post incentive compatible. That means sincere biddings in ex post Nash equilibrium, which means you don't have to know what other people's private information are. You just have to know that they're bidding sincerely with respect to some valuations. As long as you know that, sincere bidding for yourself is the best response, okay, whatever your valuation. So that's what this means, ex post incentive compatible. We want maximum surplus. Actually, we want something even stronger. We want basically to simulate the direct revelation outcome of the VCG mechanism, which in particular is maximum surplus. And then we also have this criteria of being simple, at the very least, polynomial time, okay? And so last lecture, again, at a high level, the reason this seemed like a challenge for scenario number 3 is that in particular to simulate the VCG payments didn't seem like that simple a thing. Okay, it was this difference of 2 different matchings, and we were restricting ourselves to these very simple ascending auctions. And we needed some reason to believe why ascending auctions might suffice to compute these VCG payments. So the culmination of last lecture was characterizing the VCG payments in a much simpler way than they first appeared in terms of Walrasian equilibria. So let me just remind you about them. So recall, so here Q is a vector of prices on the items. Here M is a matching between the bidders and the goods. Is a Walrasian equilibrium, or WE, if and only if. So first of all, each bidder should get a favorite good, by which I mean the item to which bidder I is matched in M should maximize its utility. So its value for the good minus the price it has to pay. If all of these are negative, then we just think of this as being the empty set. Okay? And I'll also use, on occasion, the notation for this set, the demand di of bidder I at a given vector of prices q. Okay? So this is the demand of a bidder at a set of prices in a unit demand context. And then, again, this would be trivial without any other conditions because we could just set the queues to be infinite and the matching to be empty. So it's also important that unsold goods have to have price 0. Okay, so j unsold only if q of j equals 0. Okay? And then the key result from last time, which took some work, but having done that work, we'll now just use it, which is that in fact, the VCG payments can be characterized in terms of Walrasian equilibria. So first of all, the VCG outcome is a Walrasian equilibrium. That's point number one. Second of all, among all of the prices that arise in Walrasian equilibria, and we know there can be many. So first of all, there is a smallest one, okay, which is a priori obvious. And second, actually, the VCG payments are that smallest Walrasian equilibrium. So if P of G is the VCG payment of the winner of item J, or if item J goes unsold, just define P of J to be 0, then so P of M, let's see, so where M here is the VCG allocation, is a Walrasian equilibrium, and 2, P is component-wise at least as small as any other Walrasian equilibrium price vector. Okay? And again, what was the point? The point is now rather than conceptually shooting for the VCG payments, we're going to conceptually shoot for the smallest Walrasian equilibrium. Why does that seem like progress? Because if you look at the definition of Walrasian equilibria, it feels like the kind of things that are true by the stopping condition of a descending auction. Okay, so this seems like progress, something we could plausibly compute with an ascending auction. So the point of today's lecture is to actually show you the auction which does indeed compute the smallest Walrasian equilibrium or equivalently computes the VCG prices. Okay? And let me give you a warning. My guess is, so there's going to be 2 lectures with a break as usual. I suspect the first lecture will go a little bit longer, but then the second lecture will make shorter. Okay, so we'll finish at the same time overall, but it might be a little bit front-loaded today. Okay? So any questions before we start? The next step is I'm actually going to show you the auction, and then the rest of the lecture will be analyzing it and proving that it does what we want. So any questions? All right. So the good news is that the auction itself, very simple, very attractive. It's really kind of the simplest thing you might possibly hope could work, which is great. All right, so here's the auction. We'll call it the CK auction after Crawford and Knoer. And again, a lot of this class will be very recent stuff, but last week and this week are not lectures of that form. This is old stuff. All right, so the intuition, we're just going to start with the prices being 0. There's going to be over-demanded goods, and we're just going to raise prices on over-demanded goods, and we're going to hope that supply and demand equalize at some point, and that's when we'll stop. So initially, all prices are 0, and there's going to be a notion of bidders being assigned or unassigned. So assigned means there's some item that you're tentatively the winner of. And I should say, for those of you that remember the Gale-Shapley stable matching algorithm, you might enjoy looking for parallels between this auction and stable matching. There's actually a number of them. Okay? So all bidders initially are unassigned, naturally enough. And so here's the main loop. So remember, this is an iterative auction. It's not direct revelation. So we're never going to directly ask people for their valuations. We're just going to ask people, well, given our current prices, what do you want? Meaning, which is your favorite good at the current prices? Okay, so those are going to be the queries. So for any bidder which is currently unassigned, does not have some item, we say, well, which item would you want, given the current prices? Again, we collect that information from all the unassigned bidders. Okay. So ask each unassigned I, And again, I'm going to use this notation di of q. Okay? So here, di of q is actually, if there's ties, in this definition, this is actually asking for all of the things that maximize utility. Sort of remarkably, in this auction, we actually only need one from each bidder. So each bidder can just choose an arbitrary favorite good and tell us. And again, if it doesn't want any of them, it should tell us, because if the prices are too high. Okay, so if none, all right, so either if there's no unassigned bidders, or if every unassigned bidder says, no, I don't want anything, the prices are too high, then we stop. Okay, and the tentative winners become the actual winners, and the current prices become the selling prices. Okay. So if none, halt. And again, the current allocation and prices become the final ones. Otherwise, pick some such bidder I and a good that it wants at the current prices. And we're just going to give j to I. Okay? So if you like, you can also think of this as bidder I is sort of outbidding the current holder of the good j. Okay? So assign j to I. Now, if I is the first person to ever bid on this good j in the history of the auction, then it's not kicking out at anybody else. Okay? And we also just leave the price at 0. But in the general case, it's going to be that there was some I prime who was the previous bidder on j, who had been the tentative winner. Okay? So if I outbid I prime for j, then we make I prime unassigned. And also, we bump up the price of this good. Okay? So increment q of j by epsilon, where epsilon, as usual, is just some small increment that we choose in advance of the auction. Okay? So the first bidder on a good gets it at 0. Every subsequent good changes who the winner is and bumps up the price by an epsilon. Okay? Actually, I just realized I had a typo. So when you ask people for their favorite good, actually, this doesn't make a big difference. But for lecture, I'm actually going to ask them for their favorite good at the prices q with an epsilon added everywhere. Okay, now that's almost exactly the same thing. Right? So if I add epsilon to every single price of the good, it doesn't change your favorite, except it might cause you to drop out when you weren't going to drop out before. Okay, that's the only difference. Right? But let's just do it this way. And that's it. That's the whole auction.
Upon termination, you pay the prices Q.
Let's see. No, no. Yeah, we're actually going to have you pay. Yeah. So the Q. Right. So it didn't get incremented. Exactly. Exactly. So let me just write this here. So at current allocation and prices Q. Okay? That's right. So conceptually, when we ask a bidder for its favorite, we're envisioning incrementing every single good, but really it's only the one that it actually picks that's going to get incremented. Okay? But this is going to introduce a discretization error of epsilon and a bunch of stuff, but that's all it does. Okay, so it's not a big deal. Yeah, but this is the formal description. Exactly. And because, and this was the comment, because the bidder was agreed to pick a good j at this price with the increment, then we know that it's happy to have that good, or at least it has non-negative utility for that good even after the increment. Okay? All right, so that's the whole auction. Okay? So this is it. So the rest of the lecture is just going to be proving that this does everything we want. So any questions about that? Say it again? No. So you mean here? Yeah, so in fact, this can be implemented many ways. So one thing you can do is you can just poll the unassigned ones, and as soon as anybody says they want to outbid somebody else, you stop and you go with that person. So, I singled this out because I always want to focus on, what are the queries? What is the communication between the seller and the bidders? And, at least in the maximal implementation, every single round, the subset of unassigned bidders are given a so-called demand query at the prices Q plus epsilon. Okay, but again, if you wanted to optimize it, that would be easy. So for everything to work, you just need to pick an arbitrary bidder I and an arbitrary who's unassigned and an arbitrary good J in their demand set and proceed. That's all that's necessary.
So a priori with this description, it seems like you could implement it one way and I could implement it a different way, and we might come up with different allocations, if, up to the discretization error.
Yeah, so up to the discretization error, I agree. So there's a question whenever there's, so in some sense it's underdefined, I mean, in a bunch of ways. So it's sort of amazing it works actually. So, you could pick any number of unassigned bidders, and then they could offer any number of their favorite goods. And in principle, each of those decisions can have a lot of influence over the trajectory. But in the same spirit of the Gale-Shapley stable matching result, that actually the outcome is independent of those choices, the same sort of thing's going on here. And actually, if you go back what I promised you, so what am I promising you that this is going to do? I'm promising you this is going to simulate the VCG outcome, which basically means I'm promising you that the final prices will be the VCG payments, right? So the VCG payments are obviously defined independent of any ordering here. So if I say that this always equals this one fixed thing, that's a proof that the output of this is independent. So the sequence of iterations will certainly depend on how you make these decisions, but the final output will not, which is a totally non-trivial feature of this algorithm. Okay. So again, all the complexity here is in the analysis, none in the auction, which arguably is exactly how you want it, okay, if you have to have complexity somewhere. All right, so let's start developing a feel for this auction. So first, just a couple trivial observations. So notice that if you're a bidder I and you bid on some good J, okay, you're the tentative winner, and you will continue to be the tentative winner on that good until someone outbids you. Okay? Once you're assigned, I will not ask you for further input. Okay? So the only way that you relinquish a good is by someone else taking it away from you. So then in particular, if you think about it, once a good has been bid on by a bidder, it will forevermore be tentatively assigned to somebody. Okay? So once you're tentatively assigned to someone, you always will be for the rest of the auction. Okay. So I bids on J, retains it till outbid, and then once, so if J is ever bid on, will be assigned at the end. It may change hands many times, but it's never going to be put back in the pool of unassigned goods. Okay? All right, and assuming sincere bidding, termination should be obvious. Okay? And this is always a feature of ascending auctions. It's clear you're making progress. The prices only go up. If I'm a bidder, I have some maximum willingness to pay for any item. If the prices get higher than that, well, obviously I'm going to drop out. Okay? So terminates in, let's say, the maximum valuation of any bidder over epsilon, the amount of progress we're making. This is as high as the price would ever get on a single good, and then times the number of goods m. Okay? So it's pseudo-polynomial. So if you were taking an algorithms class, this wouldn't be ideal. But for such a simple ascending auction, this is just fine. And you can imagine ways of accelerating it, like as the prices rise, you increase epsilon accordingly. We're not going to discuss optimizations. Okay? So for the basic version, termination's clear. Okay. So the first lemma is an easy one. And it's just going to confirm the intuition we've had so far that it seems like merely the Walrasian equilibrium property could probably fall out pretty easily of the first ascending auctions you'd think about that equalize supply and demand. So let's make that precise. So sincere bidding results in an epsilon Walrasian equilibrium. And on the exercise set that's due today, I asked you to prove that if you have an almost Walrasian equilibrium, you necessarily have an almost surplus maximizing allocation. Okay? So hence, close to max surplus. Okay, so you're going to be off by at most m times epsilon from the surplus. Okay, so as epsilon goes to 0, you have no surplus loss. So let's prove this is true. Okay, let's prove that epsilon will always be an equilibrium condition. Remember that what that condition is, it's the same as the normal WE condition, except you're allowed to be assigned to a good where you're off by epsilon here. Okay, so it's still going to be true that you never have negative utility, but it may be that your utility is epsilon less than if you'd gotten some other good at the current prices. Okay, that's the definition. So proof. All right, so how about this? How about this condition? Unsold goods have price 0. Why is that true? That's from here, right? So the only way you go unsold is if you were never bid on. If you were never bid on, your price is 0. Okay? So that's good. So now let's try to understand why a bidder is matched to its almost favored good. I mean, in English, very quickly, it's just because at the time you bid for a good, it was essentially your favorite, up to an epsilon. And then things only started looking better as the rest of the auction proceeded. Okay. So formally, suppose I, at the end of the algorithm, is matched to J. And here I'm allowing J to be nothing. Well, consider the last time that I was asked. Okay, the last time that I was unassigned, and it said, I want J. Okay. So I'll say when I bid for J, with the understanding that if J is the empty set, this was bidding for nothing. At that point, J, so this is some intermediate iteration of the auction, not at the end in general. Okay, so it's not the final price vector Q, it's some other price vector, but of course since it's an ascending auction, it's at some point with only lower prices. So when I bid for J, J was I's favorite at the current prices. Okay, I'm lying a little bit. Why am I lying a little bit? Yeah, up to epsilon. Right, so I asked for its favorite at Q plus epsilon everywhere, but then in fact, after the assignment, I only bumped up J's price by epsilon. Everything else stayed the same. Okay, so if it was basically tied between two goods, all of a sudden at the current prices after I sort of broke that symmetry and made the one that it got a little bit more expensive. But up to an epsilon, that was its favorite. And now here's sort of a really important property of the unit demand setting, which is that as the auction proceeds, this is only more true. Okay? So since then, all right, so this was, some iteration number 124 out of a total of 180 iterations. So what could have happened in the final 56 iterations? Okay, well, first of all, what's going on with the price of good J in those last 56 iterations? Nothing, right? The price doesn't change unless you're outbid. And I was the final winner of J, and I'm sort of rewinding to the point that it was the last bid on that good, bid on that good. And of course, it's an ascending auction, so the other goods are only getting more expensive. Okay, so this is only more true at the outset. Since then, let me just write only more true. So J's price unchanged, others going up. Good, so that's it. Okay, lemma 1. So looking ahead a little bit, so for the second lecture for today, we're going to look at a scenario 4, which is not that complicated. It'll have some different complexities than scenario 3. But then next week, we're going to culminate this whole ascending auction stuff by talking about, in some sense, the most general situation provably for which you can have these awesome ascending auctions. And so that's a setting called so-called substitutes valuations. And so just looking ahead, this is kind of the key property that defines substitutes valuation. So this is an important property that basically, at a snapshot of an ascending auction, you do your best thing, and then that remains the best thing as the auction proceeds. Okay, so that'll be the motivation for the generalization next week. Okay, so what do we know? So we have this simple auction. And the hard thing that we're trying to prove is that the outcome, assuming sincere bidding, is actually the VCG outcome. We've made some progress. We at least get the VCG allocation. Okay? We at least get a surplus maximizing allocation. We get some Walrasian equilibrium, but we really want one in particular, the smallest of them all. Okay? And that's going to be harder to prove. But that's what we're going to do next. So any questions? All right. So lemma 2. And this, okay, so lemma 2. So here's what it says. So consider the outcome of the CK auction. Okay, so final price is Q, final allocation M, and let PM star, and again, assuming sincere bidding, and PM star be the VCG outcome, assuming truthful revelation. Okay, so this is what we want to be very close to. So the claim in lemma 2 is that we're almost as low as the VCG prices. Okay? So P, we know, is the smallest exact Walrasian equilibrium. We're going to terminate with something Q, which we know is an epsilon Walrasian equilibrium, which is barely bigger than the smallest possible exact Walrasian equilibrium. Okay? That's lemma 2. And this is a little tricky. This is probably as hard as we're going to have to work today. It's all elementary, but it's a little tricky. Okay? Okay, good. So, proof. So most of the trickiness is just in the setup, actually. Okay, so we're going to have an inductive, it's going to be an inductive argument. So give me a second just to sort of set up the appropriate induction. So consider the first time. So intuitively what we're going to say is, in this CK auction, a red flag kind of goes off. So imagine we're just running this, and imagine we knew what P was, the VCG prices were. Okay, and imagine we're sort of tracking the prices of all the goods. And the current price of some good J starts drifting upward further and further, and it starts being a little bit above the VCG price P, and then it starts being more and more above this VCG price P. Okay? So I'm going to parameterize that. So let's consider the first time that we have a good whose price is significantly above P, and it's about to get bumped up even further. Okay, so some bidder's about to bid on this seemingly quite expensive good. So consider the first time a bidder, call it I1, is about to bid on a good J1 with the current price, and again, this is not at the end of the auction, this is somewhere in the middle, so I'm going to use a different letter R. Q is the prices of termination, R is in the middle. So a price RJ, and so that the current price is already sort of significantly bigger than P of J, the VCG price. Okay, so let's just say epsilon times L. L here is a parameter. Okay, so think of it as like 10 or something. Okay, so it's already drifted above the VCG price, it's about to go even further. Okay? So here's the key claim. So basically what I'm going to do is I'm going to give an inductive construction, okay, parameterized by L. The induction will have L steps, and it'll be evident that it'll be patently obvious that the maximum number of steps I could run this induction without a contradiction is for L being up to the number of goods that could possibly be traded. Okay, and of course, you should think of min of NM. This is the number of bidders, this is the number of goods. That's just the edges in a maximum matching. Okay. All right, so claim. So suppose this is true. Suppose this is about to happen for some L. Then I claim for all positive integers k between 1 and L inclusive, I can show you a nested set of bidders getting bigger and bigger, a nested set of goods getting bigger and bigger, satisfying a few properties. Okay? So set UK of k goods. I said BK of k plus 1 bidders. Okay, so there's always going to be one more bidder than goods that satisfies the following properties. Why these properties? Because these properties were the slickest proof I could figure out. Okay? Don't really have a better explanation for you. So, okay, so for all bidders in this set UK, sorry, for all goods in the set UK, all of the prices of these goods are high. Okay, so we're starting from the assumption that there's one good with a high price. Sorry, this should be J1. So there's one good J1 with a high price. That's going to be the base case. And I'm going to show you bigger and bigger sets of goods, all of whom are overpriced. Okay? So I'm going to lose an epsilon each time I add a good, but still, I'm going to give you these big sets of goods, all of whose prices are too high. So R of J is greater than the V. So always remember P are the VCG prices, the smallest while R is in equilibrium. Okay. Pj plus epsilon, and then again I'm going to lose a little bit in every step of the induction. Okay. So when k equal 1 is going to be the base case, and that's just sort of the same thing I was assuming. Every time I bump up k, I'm going to lose a little bit in how overpriced all of these goods are. So 2, for all bidders in the kth set, the most recent bid by I is for a good in UK. Okay, so I'm going to show you k plus 1 bidders, all of whom most recently bid for some good in these k goods of UK. Okay, and I should be a little bit clear here. So I'm including, so there's a little bit of time incoherence. So the price R, so remember, we're basically freezing the algorithm at auction when this bidder I1 is about to bid on this good J1. Okay? So R, again, these all only matter for the epsilon, so it's not a big deal. But just to be precise, R are the prices before we increment J1 by epsilon. And when I say most recent bids, I'm including I1's bid on J1. Okay? So this bid set is sort of after I1 is bid on J1, and the price R is before that's happened. Okay? All right, so 3, all of the bidders in BK are matched in the VCG outcome, in the VCG allocation M star. Okay? So these are 3 properties. And I think once I show you the base case, it'll be more clear. There's one thing I want to observe right now. So suppose I can do this. Okay, so suppose I prove to you this claim. Then in particular, remember BK has k plus 1 bidders. And property 3 says all of these k plus 1 bidders are matched in the VCG outcome M star. Okay? Well, k plus 1 can't be bigger than the minimum of M and N. Right? Only the minimum of M and N goods can be traded. Okay? So this says I'm only going to be able to do this construction for L at most min of N minus 1. Okay? So if proved implies that L is strictly less than the minimum of M and N, then we'll be done. Okay? So the one thing I want you to observe is I've reduced the proof of lemma 2 to this inductive construction. Okay? Assuming this, then I can exhibit these nested families of sets for you. Agreed? Okay. And from here it's pretty straightforward. There's some nice cute ideas, but it's pretty straightforward once you have the inductive setup. Okay. All right. So then here's the construction. So the base case, you can guess what it is, but there's actually one thing we do have to prove. So we're going to take, all right, yeah. So for the base case, we need one good. So k equals 1. We need one good and we need two bidders. Okay? All right, so let I2 be the current bidder on J1. Okay, so remember where we are. This bidder I1 is about to bid on J1 even though J1's already expensive. So I claim that actually it must be displacing a bidder I2. Okay, that there must be someone who would previously bid on that, some tentative winner, I2. I2 exists. Why does I2 exist?
J1 is at least epsilon.
Exactly, I heard it from a bunch of people. So in particular, this assumption implies that the current price of the good J1 is positive. So someone bid on it at some point, so someone's its tentative winner right now. Okay, so I2 exists. All right, good. And so now what are we going to do? We're going to set the good set just to be equal to J1. And by hypothesis, 1 holds. So no problem there. We set the current bid set to just be I1, I2. I2's most recent bid was on J1. I1 is about to bid on J1. We're going to count that. So property 2 holds. But we do have to prove property 3. Okay, so I have to argue. So remember, this is in the VCG outcome M star. Well, this may seem a little weird, actually, right? Because we're arguing about the CK auction, which is doing its thing. And now I'm sort of watching the trajectory of the CK auction and then arguing about what's up with those bidders in the VCG outcome. Okay, but I really need that as a reference point. Okay, so I need to prove that. So proof of 3. All right. So why is this true? Okay. All right. So first I claim that that's not what I want. That should be J1. Both of these bidders in question, I1 and I2, their value for the good J1, the ones that they bid on most recently, well, it's got to be more than the VCG price of J1. Why is that? Well, okay, they just bid for it in the CK auction, right? So at the current price in the CK auction, which is R, right, that's how expensive this good is, they wanted it. They preferred to have that good to just dropping out of the auction. So their value have to be at least to the current CK price R, which by assumption is significantly bigger than the VCG price P. And what does that mean? Well, so now I want you to remember that the VCG outcome is a Walrasian equilibrium. Okay? Which means if you asked any bidder, is it happy with what it's matched to at the current prices, which in this case we're doing a thought experiment for P, it would say, yeah, I'm happy. So in particular, if someone is unassigned, they better be happy being unassigned. Okay? But given that I1 and I2's value is bigger than the price of J1, there's no way they'd be happy being unassigned in M star. Okay, so they get strictly positive utility if they're matched to J1, so they have to get strictly positive utility in this outcome, so they have to be matched. Okay? All right, so that's the proof of the base case. Any questions about that? So now I got to show you how I can keep building up these sets of goods, the U's, and bidders, the B's, by 1, and each time I build them up by one new sort of resident, I'm allowed to lose an epsilon in how expensive those goods are. Okay, so that's the game now to push through the inductive hypothesis. Okay, so inductive step. So we're given UK minus 1 and BK minus 1, satisfying 1 through 3. So we're going to start by finding a good to add, another item. Okay, so we want to supplement UK minus 1 by one new good. So here's what we're going to do. We're going to say, well, we have these, the number of bidders in the last set outnumber the number of goods. Moreover, all of these bidders have to be matched to something in the VCG outcome. Okay, so from the last step, from iteration k-1, we have these k bidders. They're matched to k, obviously distinct goods in M star. And our special set of goods, UK-1, only has k-1 goods. Okay, so there has to be something outside that set. So, saying it again, by the inductive hypothesis, there is a bidder I in our bidder set amongst our k bidders in BK-1 that's matched to a good outside, we're going to call it JK, outside of UK-1 in the VCG outcome M star. Okay? That's just pigeonhole principle. Now, let's try to reason about, well, the other thing is, remember from property 2, last time we asked this bidder I what it wanted, it didn't want good JK. Right? There's this good it's sort of rightfully supposed to have in the VCG outcome, and it avoided it. It said, no, 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 I'd rather have this other good, which is in UK-1. So let's try to understand why did it do that. Intuitively, the reason is because whatever the good was in UK-1, it looked cheap compared to good JK, right? But we also know that sort of everything in UK is really expensive, using VCG prices as a reference point. So it must be that the good it's supposed to have, JK, is even more expensive, up to an epsilon. Okay, so that's sort of the argument. But let me just make that precise.
We're going to throw that good into UK-1.
Yeah, right. So hopefully the labeling JK suggested that would be what we'd add to UK-1. And what I'm about to do is I'm going to argue that it's okay. So I've already argued that at least it's a different good, so at least they get a bigger set. But remember, we have this property here on UK, right? So for the inductive step, I need to make sure that this is okay. So in other words, I have to argue that JK is expensive with respect to the VCG prices. Intuitively, the reason that's true is because if it wasn't expensive, this bidder I would have bid on it and not bid on this other thing in UK-1. Okay? And so that's all to get property 1 to go through for the inductive step. All right, but just let me just quickly do this. I mean, this is really where we use the kind of Walrazian equilibrium property of the CK auction. So let me just spell it out. Where did I go? Oh yeah. So question, why did I last bid on a good J in UK-1 instead of on JK? Okay. Well, so it must have been that J looked better. So I'm going to write this in terms of the prices are, which I'll explain in a second. So there's actually two different things going on here, so let me explain them one at a time. So first of all, suppose I replace the R's with a different letter, S, which were the prices at the time that this bidder I, all right, so remember, bidder I's most recent bid was for this good J. Okay? So we have this bidder I. At some point, most recently in the auction, it bid for some good. By the inductive hypothesis, we know that good is in UK-1. I'm calling that good J. Okay, so J is the most recent thing that I professed interest in. All right? So at the prices at that time, whatever they were, if the prices were S, then by definition, J was the favorite good of I at those prices S, up to an epsilon. Okay? Because we just asked, what's your favorite good? And it said J. Now, since then, more stuff has happened. We don't have those prices S, we have these other prices R. But just like in lemma 1, this decision is only better than ever. Okay? So the price for this good, J, has not gone up, and the price for this other good, JK, may have gone up. So again, this is only more true with respect to the prices R. Okay? So this is the combination of the fact that I bid for J plus the fact that we have ascending prices and that prices don't ascend when you've got a good. Okay, so that's true. On the other hand, at prices P, Okay, so in the matching M star, the VCG outcome M star, I is matched to JK. And because this is a Lavoisian equilibrium where the price is P, I prefers JK to anything else, in particular to this good J. Okay, so but since P M star a Lavoisian equilibrium, we get the reverse inequality if I switch the R's to P's. Okay. So again, this is just because people bid on their most preferred goods up to an epsilon, and this is by the Lavoisian equilibrium condition applied to the VCG outcome. So how is this possible? How is it possible that when we switch the prices from P to R, I's relative preference between J and JK flips? Well, it has to be that if I think of going from, let's say which one's higher. So the R's are the higher ones. So it has to be that if I switch from P to R, why would I switch from JK to J? It has to be that the price on JK goes up by more than the amount that the price went up on J. Okay, so price is P, I like JK, I increase all the prices to R. Why does it flip? It's because relatively speaking, the increase in price on JK is more than that on J, up to the epsilon. Okay? If you like, you can just add these two inequalities, cancel all the V's and rearrange, you'll get exactly the same thing if you prefer an algebraic manipulation. Okay? So all this stuff implies that, but again, the extent to which JK is marked up over the reference point of the VCG prices. Right, so again, switching from P to R, your favorite switches from JK to J. So the increase on JK has to be bigger than the increase on J, again, up to an epsilon. Okay. Now J was in this set of goods we inherited from the last iteration, UK minus 1. The inductive hypothesis says those are all expensive. Okay, everything in UK minus 1, in particular J, is expensive. So this is just saying JK is as expensive, up to an epsilon. Okay. So inductive hypothesis, L minus K minus 1 plus 1, also known as epsilon L minus K. Okay. And so again, the whole point of this was just saying we can add this good JK to our old good set. Okay, and again, what was the problem? Why might that screw us up? Well, we have to preserve this property that all goods in our special good set are expensive, and that's what we just proved. Okay? So, setting UK equal to the last set of goods plus this new good we just identified JK satisfies 1. Okay? So that's one of the main two things I had to show you. I added a new good to the good set. Now I have to add a new bidder to the bid set. Okay, that's the main other step of the inductive part. Okay, so I showed you where I get my kth good from. Where do I get my k plus first bidder from to push through the inductive step? All right, well, so JK, its price is bigger, right? What did we just prove? We just proved that JK's price is bigger than that at the VCG prices. So in particular, it's positive. This good that we just added. Oh, so I should say, all right, so adding a new good, we had to make sure it was expensive. Adding a new bidder, what are we worried about? Okay, what do we have to preserve? We have to make sure that when we add a new bidder, it was most recently interested in some good in our set UK. And then we also have to make sure that it's matched in the VCG outcome. Right? So this is what we have to keep our eye on. Okay, so, but if the price of this good we just added JK is positive, again, as we discussed, there must be some current tentative winner on it. Okay, that means people were bidding on it, so someone most recently bid on it. And there exists a bidder, IK plus 1, the most recent bidder on the most recent bidder on JK. And now importantly, this is not one of my old bidders. Okay, so this is what I want to add. I want to augment the bidder set by this. And bidder IK plus 1 is not a member of BK minus 1. You see why? I know it's a lot to keep track of. Good. And which property are we using here? Property 2. Okay? So we're using the fact that the K bidders we had before, all of their most recent bids went just to the K minus 1 goods in UK minus 1. JK is this new good, so none of our old bidders most recently bid for JK. It has to be somebody else. I'm calling that IK plus 1. Okay. Excellent. And so this is who we're going to add. And currently assigned to it. And so that means we're allowed to define, at least for the perspective of property 2, we can define BK to be BK minus 1 plus this new person. IK plus 1. Okay? Now there is this final property 3, which is that this new person we just added has to be matched in the VCG allocation M star. The proof of 3 is exactly the same as the proof was in the base case. Okay? So basically it's bidding on this good at a price which is even higher than at the VCG price. So that means with respect to the VCG prices, there's certainly something that it strictly wants, so it can't be unmatched. It has to be matched to something. Okay, so same as the base case. Okay. So that proves this inductive claim that if something is too high by L multiples of epsilon, I can construct these sets. Okay, I can keep constructing bigger and bigger bidders, all of whom are matched in the VCG outcomes. There can only be the minimum of NM of them. So that's the most over pricing we're ever going to do a result by the CK algorithm. So as epsilon goes to 0, we really are getting the minimum VCG prices, or at least we're below the minimum VCG prices. Okay. All right, QED. Questions? Like I said, that's probably that should be the hardest thing for the day. So, should learn my lesson from last week. I'm trying to put the hardest things kind of more in the early part than at the end. So, always still have some energy. Okay. So that's really cool. All right. So it really doesn't, frankly, to me, intuitively, it doesn't feel like the auction, it does feel like it's explicitly engineered to terminate a Lavoisian equilibrium, but it doesn't feel like there was intentional work to go into being so parsimonious about it, to actually, convert it into the minimal ones. Yes, you got to grant that it starts at 0, so it starts underneath all of the Lavoisian equilibria, and somehow that's enough to make sure you don't ever kind of shoot into the interior of the set of Lavoisian equilibria, which is really cool, I think. All right, so for the incentives part, which I'm about to move on to, we need actually a sort of two-sided bound. Because strictly speaking, so what do we prove? We prove that any exact Lavoisian equilibrium can only be higher than the VCG prices. Okay, but the CK auction isn't actually computing, it's not terminating with an exact Lavoisian equilibrium, it's terminating with an epsilon approximate one. Okay, so we haven't, strictly speaking, proved that it couldn't be way lower than VCG prices. And as we'll see, that would actually be a problem for incentives. But intuitively, you wouldn't think so, and it's not. So I'm going to state this lemma. The proof of this lemma is very similar to the proof we just did, and I've sort of chopped it into morsel-sized pieces on the exercise set. You can go through it there. It's a very similar flavor. So here's the statement. The statement is that any epsilon Lavoisian equilibrium, whether the one computed by this auction or not, can't be significantly lower than the VCG payments. Okay, so just throwing in an epsilon doesn't really change the fact that you can't be smaller than the VCG payments. So let QM be any Lavoisian equilibrium, and let PM star be the VCG outcome, then be minus. You can be a little bit less than the VCG prices, but not by much. Just by the same amount. Epsilon times potentially the number of bidder item matches. Okay, the minimum of the number of players and the number of bidders. Okay. So we will use this lemma. Okay, so we'll see. We'll use this when we talk about incentives, but the proof I'm not going to do here. Okay. There's a similar inductive build up the sets proof of this lemma as well. Okay. All right, so let's take a step back. Let's take stock of what we've got and what we want, and what's the gap in between them. So upshot, notice all of this analysis has been done assuming that bidders bid sincerely. Whenever we ask them what their favorite good is at the current prices, they tell us honestly. Okay, this has all just been, in effect, a thought experiment, kind of crossing our fingers. If people behave this way, then what happens? And so now, sort of the most important thing is to understand, is there any justification in that assumption? Okay, is there any reason for bidders to bid sincerely? And, right. So, but is sincere bidding an ex post Nash equilibrium? Again, up to some small error, or not. So one thing one thing worth just thinking about a little bit, and there's an exercise on this also, which is merely by virtue of the fact of sincere bidding leading to the VCG outcome, maybe that's enough. Right, so maybe just simulating the VCG outcome in an indirect auction is a sufficient condition for having a ex post and setting compatible implementation. It's a little bit of a subtle question. It kind of depends on the context a little bit, but that's just something to keep in mind. I've been trying to argue, I haven't given you all of the rigorous backing yet, but I've been trying to sort of direct you into thinking that it's a necessary condition, right? So if we want an ex post and setting compatible implementation that's surplus maximizing, I've basically told you, without a full proof yet, that we have to at least do this. Now that we've actually succeeded for a problem we care about, the question is it enough? Okay, so what I want to do next is kind of help you kind of understand that question a little bit more and what is involved, say for the scenario 3, in passing from what we've proved so far and what we want. Okay. So let's start with just kind of what you get for free from proving that sincere bidding gives you a VCG outcome. So let me define. So recall, we discussed these indirect implementations last week, so just to remind you, so when you have an iterative auction, there's this notion of an action, which is what you do, okay? Like how you bid at each round as a function of everything you know and everything you've seen so far. Then there's the notion of a strategy, and remember, a strategy is a function from your private information, your valuation, to an action. So as a function of what you want, how do you behave? So for example, sincere bidding, if you think about it, it's really a function. It's really a strategy. It's not an action, right? Because your answer to a query depends on your value. Okay, so knowing your value, you know how to act. Okay. So what I'm now going to do is I'm going to define a subset of strategies. Okay. So a particular strategy, a function from values to actions, I will call consistent. No, excuse me. This is an action. So consistent action is defined as the result of sincere bidding with respect to some private valuation. Okay? So in other words, think about this. Suppose you have some player and you have no idea what they want. You have no idea what their valuation is. But you just observe how they act, how they answer these queries. Okay? Then you can answer the question, is this a consistent action or not? I can say yes, because I can envision a valuation with respect to which this would be the outcome of sincere bidding. Okay? I can't just watching the action. There's no way I don't have enough information to say, is this person bidding sincerely or not? Because I don't know their valuation. I only see, in effect, the range of their function. I don't see the domain. Okay? So an action is defined as a consistent one if it could arise from sincere bidding, if there's a valuation for which this is how the player would act. Okay? All right? So now here's kind of here's what you get for free from simulating the VCG outcome. So let A be an iterative auction with this property, such that sincere bidding gives you the VCG outcome. So if other players, here's the claim, if other players bid sincerely, okay, so suppose you're player I, and you know other players are bidding sincerely. You could bid sincerely, or if you get a higher payoff from some other action, you'd do that as well. Okay? So what do you think the rest of this proposition is? I want to say it's never in your interest to deviate from sincere bidding. And so I'm going to make a weaker statement. It's never in your best interest to deviate in a particular way from sincere bidding. So the claim is it's never in your interest to deviate to a consistent action. So again, when you're formulating how you might act in an auction, you have a bunch of options, right? So one thing you could do is you could just be honest. Right? That's the easiest thing. Here's one form of deviation. Well, let me actually up front pretend like I have a different valuation than I do, and then I'm just going to act consistently with this incorrect valuation, with this false valuation. Okay, that's another way I could act, which is not truthful. It's a deviation. A third thing I could do is just something crazy. And we saw an example last week. Remember, we had parallel English auctions. I wanted to convince you that you didn't have a dominant strategy equilibrium. And the way I convinced you is I had the second bidder act in this crazy way. The second bidder monitored what the first bidder did in the first iteration and then conditioned on that and then behaved in totally different ways after that. Okay? So that's a still third kind of action, which is not a consistent action. There is no valuation with respect to which sincere bidding would lead to that crazy second bidder from last week. Okay? So what you get for free here is if sincere bidding leads to a VCG outcome, then this sort of this intermediate deviation is never helpful. It's never helpful to just say, well, let me pretend like I have this other valuation and then bid sincerely with respect to it. Okay? That's not going to do you any good. So if other bidders bid sincerely, can't gain from any consistent action. Okay? So do you see why you get that for free when an auction has this property? Anyone want to suggest it's kind of a one-sentence English reason? I mean, in effect, right, so what do we know about VCG? We know VCG is dominant strategy and center compatible, right? So we know that, in the direct revelation version, at least, if you declared an incorrect deviation, it wouldn't help you, okay? And so the point is, if with sincere bidding, this auction A is simulating the VCG outcome, okay? So then if you bid truthfully, it just simulates the truthful VCG outcome. If you just bid with some other consistent action, it's exactly as if you bid the corresponding valuation, V prime, to the VCG mechanism, which doesn't help. Okay? So in other words, when you have an auction with this property, that it simulates the VCG outcome with sincere bidding, it introduces a very strong bijection between, on the one hand, when everybody plays a consistent action in the iterative auction, and then the possible strategy profiles, direct revelation profiles in the VCG mechanism. Okay, there's a one-to-one correspondence that preserves bidders' utilities. Okay? So that means deviations amongst consistent actions correspond to deviations in VCG, and those never help. Okay? So let me just write a little bit about that. Where are we? Okay, so reason So consistent actions in A. And so this is utility preserving. Strategy profiles, or maybe I'll even just say bid profiles in VCG. So i.e., we're just inheriting this property from the fact that VCG is dominant strategy semi-compatible. Okay? So that's what we get for free. Now this is not the same thing as saying this is weaker than saying the auction A is ex post and semi-compatible. It's weaker than saying sincere bidding is an ex post Nash equilibrium. Because again, to be an ex post Nash equilibrium, that says, look, I'm bidder I. And it should be the case that if I know, first of all, that other players are bidding sincerely, and second of all, again, for the purpose of this thought experiment, I even think of that I know their valuation, it should be that my best response among any action I could do, consistent or inconsistent, should be to just answer all the queries truthfully. Okay, so what you have to prove is that even if a bidder, so you assume all the other bidders bid sincerely, you have to prove that even if this bidder bids in a crazy way, inconsistent with any valuation, even then their payoff doesn't go up. Okay? So there's going to be an exercise saying that actually there are, if you want a pathological action where you can separate these two things, you can. Okay? So there are auctions A that have this property, and therefore consistent actions don't help, but inconsistent actions could help. That's in principle possible. And that means that when it's not possible, you have to prove something. There has to be something special about the auction that lets you argue not just about consistent actions, but more generally about all actions. And that's what I still owe you for the CK auction. So that's the last part of the first lecture today. Okay? So is all that clear? So that's the issue. Good. All right. So, right, so last theorem for the first lecture is that the CK auction, happily, is more generally epic. And again, up to, up to small error. And again, just to be clear, this property you get for free is weaker than epic. So epic is not automatic just because you simulate the VCG outcome with sincere bidding. Okay, so it requires a proof. All right. So fix the bidder who's contemplating its arbitrarily crazy actions. Fix the valuation profile. And assume others bid sincerely. Right, that's the one thing we get to assume. Okay, so the other players are not doing crazy actions, and we want to prove that I has no incentive to do a crazy action either. And so again, what we know is that consistent actions don't help. Okay. So the plan is to basically prove that for any deviation which is not necessarily a consistent action, I can exhibit to you another deviation which is a consistent action, which is just as effective. Okay, so I'm going to sort of reduce the inconsistent case to the consistent case. So plan, inconsistent ones know better. All right? So consider an arbitrary deviation by I. And let's just sort of notice a couple trivial things. So first of all, the auction is going to terminate. I can't really do anything about that. Right, all the other bidders will drop out because they're bidding sincerely once the price gets sufficiently high. And from I's perspective, there's no way this was helpful unless it gets some good. Right? Otherwise, it has zero utility. So let's suppose it deviates in some way, and at the end of the day, it gets a good J.
following this specified crazy strategy.
When following the specified crazy strategy. Exactly. So, and now what I want to prove is that, it did whatever it did for it to be a conceivably interesting deviation. At termination, it got some good J. But the intuition is, well, surely there's much more just direct ways of getting this good J. Like, why not just bid $1 billion? If that's what you wanted at the end of the day from this auction, why not just bid $1 billion for good J and nothing for anything else? Like, you're going to get J at the end of the day. Now, it still requires a proof. I don't see why this is totally trivial. It does work. It is true. So I's actual valuation is V sub I. V prime is going to represent some consistent deviation it could have done. Okay, so I'm going to define V prime in the obvious way. So for good J, it's just sufficiently large, plus infinity, let's call it. And for any other good, it's going to be 0. So one deviation would be I pretend my valuation is V prime, and then I bid sincerely. And that would be a consistent deviation, and these are the ones that we know don't help. Okay? So if I can show that the inconsistent one is no better than doing this, we're done. Okay. So claim. Oh, yeah. And so then, yeah. So let QM be the final outcome with this arbitrarily crazy deviation. Okay, so this is the outcome in which I gets J. In general, there's some matching M, and there's some final price vector Q. So here's the claim, which is that if the true valuations really were V prime for I, and everybody else with a standard deviation V minus I, then the outcome of the CK auction would be a Walrasian equilibrium, or an epsilon 1, with respect to this artificial valuation profile I just defined. Okay. So QM is an epsilon Walrasian equilibrium for V prime I, V minus I. So just to be clear, I mean, the reason, so if you see some trivial reason how to finish the rest of the proof, I'd love to know it. Okay, as far as I can see, the issue is that you somehow have to say that crazy actions can't let you get a good J at a lower price than you would have gotten it had you just bid consistently with V prime. I don't think it's obvious that you can't manipulate the price downward in this auction with inconsistent actions. You can't, I'm about to prove that to you, but I don't see an obvious reason why you can't force the price downward. It seems like you have to use some of the theory we've developed. Okay, so why is this true? And anyway, so in Walrasian equilibria, we have a lot of control over their prices and how they relate to other prices, so that's the route we're going to use. So is the claim clear? So again, V prime is fictitious. Okay, I looked at I's deviation, then I invented V prime. These are other people's valuations, and then this is a well-defined state. Okay. All right, so so it's certainly still true that unsold goods have price 0. There's nothing I can do about that, right? So by the rules of the auction, if I does something crazy and it bids for some good, it has that good forever. Okay, there's nothing you can do about it. So this property of the CK auction persists. It's clear that I gets its fave good in the hypothetical world where it had the valuation V prime I. And then for the other bidders, it's the same reason as ever. It's just the termination condition of the CK auction, right? So if there was some bidder, I prime, that was getting a good that was not its epsilon favorite, so again, it's the same reason, right? So think about the last time they bid, right? It was their favorite, and then again, there's price is still only a sen for everybody else. Again, there's nothing that this deviator I can do about that. Okay. So let me just write other bidders, epsilon happy, for usual reasons. Okay. So that's just a quick claim. So whatever I does, it can't prevent the fact of this auction terminating with this Walrasian equilibrium with respect to some valuation profile, okay, where V prime is just meant to sort of indicate what it seems like I wanted by its deviation. Okay. So again, what we want to argue is that these prices can't be too low. What we're worried about I doing is somehow acquiring this good J at a super low price. Okay? So why can't that happen? Well, it can't prevent the fact that you go to a Walrasian equilibrium. And remember this lemma 3. This was the one I skipped. Okay, lemma 2 that we worked hard to prove says that Walrasian equilibria outputted by the CK auction can't drift much above VCG prices. And we knew we needed that. But remember we also had this complementary lemma 3, which is that, by the way, with an epsilon Walrasian equilibrium, you're not going to be really lower at all than the VCG prices. So we're going to use that here. Okay? So we know it terminates at a Walrasian equilibria. Lemma 3 is what tells us that those can't be very low, just by virtue of being a Walrasian equilibrium. Okay, so by lemma 3, the outcome of the CK auction is at least, let me write it as P prime. So here I'm defining P prime to be VCG payments for V prime I, V minus I, minus epsilon times the number of trades that might happen. So again, these Walrasian equilibria Q cannot be too low with respect to this VCG price vector. So let's now do the full comparison. So this will wrap up the proof. The full comparison of this deviator's utility with this crazy action resulting in this Walrasian equilibrium Q comma M versus if it had just bid sincerely. Okay. So utility of I in QM well, so the payments are almost the same as with respect to the VCG outcome with this valuation profile. So utility of I in VCG with the bid profile V prime I V minus I. So again, what this is saying is that basically, this is really what we want. It says this crazy action and this indirect auction isn't really doing much more than misreport in the VCG mechanism, which we know can't really help. So this is just by VCG being DSIC, utility of I in VCG with the honest valuation profile. And then again here, now it's not the case that the CK auction actually exactly simulates this outcome, but it simulates this outcome up to an epsilon times the usual factor. Okay. So util of I bidding sincerely in CK. Oh, sorry, there should be a plus blah, blah, blah. And then this gets carried down here. And down here becomes gets doubled, yeah. Okay. And so that's that. In the end, we just argued directly. Whatever action you do, it results in some QM, which is some Walrasian equilibrium, and it can only save you some vanishingly small additive factor over what bidding sincerely did. Okay. So that shows that you get robustness not just against these consistent deviations, but against arbitrary ones. So that gives us what we wanted, an awesome ascending auction for unit demand bidders.